In yesterday's lecture, we tried to answer several questions concerning the nature of industrial engineering and pointing out the differences between the practice of industrial engineering and other engineering disciplines. And we made the point that the main difference between traditional engineering and industrial engineering and operational research type of inquiry is that the method used in these two classes of inquiry are different in the sense that in classical engineering, mostly analysis is sufficient in most cases to arrive at an improvement or at a solution. But in industrial engineering practice, we don't have the same opportunities as other engineers do to take a piece of the real world, remove it from its location, from its context, and take it into a laboratory and study it in the laboratory. We don't have this possibility, obviously. So we don't have the full possibilities of trying to analyze a whole into its parts and studying the parts independently and one by one. And this is the conclusion of all this is that analysis is important in industrial engineering, but it is not enough. It's not sufficient. Lütfen geç gelmeyin. Bakın her gün bunu bana söyletmeyin. Lütfen geç gelmeyin. And so this is the central idea that instead of looking at the parts of a piece of the real world, in industrial engineering and OR, we look at first the larger system of which what we are interested is a part. That's what it says here. To understand an open system, we need to look at the larger system of which it is a part. This is the central idea of systems thinking. Therefore, systems thinking does not reject analysis. We know that analysis is important because it provides knowledge, as it says at the top, but it doesn't provide understanding of a system. Therefore, systems thinking is something which includes analysis, but is more than analysis. That's, I think, where we stopped yesterday. So let's go on from here by trying to clear out some confusions or misunderstandings about the terms that we use. One of them is this one. It's not just about terms, it's about our profession. Industrial engineering, operational research, management science. How are these related? Can we use one for the other, or what is it? Management science actually is the title of the textbook, as you have seen, perhaps. It says management science, decision-making through systems thinking. So although it is not used a lot in recent years, it's also a term that was used a lot in the past, management science. Now, operational research, I'm not going to define these. I'm just trying to point out the relation between these. Operational research provides what we can call the scientific basis of industrial engineering. I mean, we have a fair idea of what science is. Mostly, it uses the language of mathematics. Of course, science is more than mathematics. I mean, although it uses the language of mathematics and logic, it also relies on experiments and observations, okay? And operational research provides this sort of content in the industrial engineering area, okay? It's just the scientific basis of industrial engineering. The mathematical models and techniques that we teach here and that are used by industrial engineers are primarily operational research models and techniques. Now, in our department, there are 3 required courses on OR 1, 2, 3. I think you have all taken these 3 now. But it doesn't mean that the other courses you are taking, such as simulation, a course on simulation perhaps, or courses on production planning, etc., these are not independent of OR. The models and techniques that we try to study in such courses can also be called OR models. So OR is very pervasive. Alongside statistics, probability, and economics, engineering economics, microeconomics, etc., that you take in the department. All the rest can be subsumed under the title of operational research. When you, next year, when you are in the final year, you will be taking, I think, I'm not sure about the number, but two technical electives in the first semester and maybe 2 in the next semester. So there will be many technical electives for you to take. Most of these have titles like combinatorial optimization, decision analysis, multi-criteria decision making, etc. But they are all actually types include OR models and OR techniques. So OR is not confined just to the 3 courses you take, but all the other technical courses actually have OR content. Now, in the past, industrial engineering was more concerned with the engineering applications of OR. Actually, not only in the past, but also at the present, I mean, I think we have in Turkey now more than 50 industrial engineering departments. We have hundreds of universities, 50 or 60, maybe even more industrial engineering. Not all these departments have the same curriculum. Even the curricula may be different instead of being similar in some cases. And some of these departments and some practicing industrial engineers stick to the traditional areas of industrial engineering, which we can call something like production problems, issues and problems in production systems. And that's what we mean by, in the past, IE was more concerned with engineering applications. OR is more general. OR is used or is applied in any problem situation where you have to make decisions. OR is actually has been proposed as a science of decision making, and decisions have to be made in all organizations all the time. This is the central problem of all organizations. So OR is very, very, how can I call it, ambitious in its foundation, in claiming that we can find and arrive at and implement optimal solutions in each and every decision making situation with the help of science. It's very, very, how can I call it, this is a big claim on the part of OR. So OR can be assumed to be applied to more than the traditional domain of industrial engineering. But this has changed a lot. I mean, we are in constant touch with our graduates. I think our department has produced now, I don't know the number, but maybe 3,000 graduates. And we sometimes administer surveys to our graduates, trying to find out in what sort of area they are working, what sort of jobs they have, how much money they are making, etc. And from these, we understand that they do not stick to these industrial traditional areas, but work in all sectors of the industry. So that's what I mean. IE now deals with almost all applications of operational research alongside traditional engineering. So that's the relation between IE and OR. Of course, OR is not recognized as a profession, and it doesn't have, I mean, formally as a profession, because we have, for example, chambers for industrial engineering and other engineering disciplines, but we don't have, we have an OR society. There is an OR society of Turkey. And the education in OR actually in Turkey is older than industrial engineering education. OR was introduced as a program, degree program in this university for the first time in Turkey before the industrial engineering department was established in, I think, 1960. I'm not sure about the date, in the 1960s by Halim Doğrusöz, Professor Doğrusöz. Management science is just another term for OR. I will, maybe the story is interesting for you. Let me just tell you the story of this. When the war ended, when the Second World War ended, people who worked as OR analysts within the Army, and together with the Army, as I have told you in the first introduction lecture, in England and also in America. These people, of course, were discharged from the Army, and they went to civilian jobs in the industry. And they started to apply the OR techniques that they learned for military applications. They started to implement these in civilian organizations, in production systems, in companies. And then they decided to form a society. Well, the first OR society was founded in Britain, but later on the Americans also decided to establish a society. And then they came together and started to write down the rules and the rules for joining the society. How would the society be organized, offices, etc., etc. And there was a problem of a difference of opinion. Some of them said, well, only people who have served in the Army should be elected as officers of the society. And another group said, this is nonsense. It's not necessary to be an ex-Army officer to be elected to the officer as the officer of a civil society. And so this difference of opinion was so important for those people. I don't know why. This, I think, happened in early 1950s. In America, they established two different societies. One was called the Operations Research Society of America, ORSA. It's a very famous organization. The other one was called the Management Science Institute. The difference of terms management science and OR comes from this difference of opinion. Both societies became very prestigious, very famous because of their scientific publications for many, many years. And I think, I don't know the exact date, some years ago, not more than maybe about 10 years ago, these two societies joined together, and there's just one society now in America. What is it called? It is the most important society for your profession. What's the name of it? INFORMS. INFORMS. INFORMS is Institute for Operational Research and Management Science. They are still keeping OR and MS together. INFORMS. So management science is just another term for operational research. Well, let's now move over to systems thinking and start little by little to find out what system thinking is. Who needs systems thinking? We have already answered this question in educational programs for industrial engineering. We pursue two dual purposes. One is to provide mastery of quantitative analysis and mathematical modeling. And the other one is building systems thinking skills in order to be able to implement this knowledge of quantitative analysis properly. The quantitative analysis, etc., are like operational research, probability theory, statistics, economics, etc. Okay, so we need systems thinking for this purpose. Now, instead of describing or trying to define systems thinking, we start by looking at, from the textbook, 5 real-life problems and try to understand characteristics common to all of these problems. And with the help of these examples, actually, we shall be better able to understand and appreciate what sort of difficulties there are and why systems thinking is necessary to address these difficulties. Now, these 5 real-life examples are from the textbook, and the textbook explains these in detail. Now, if you remember, I told you in the first lecture 0 that preliminary preparation is useful. Actually, it is required. And I have given you the lectures and the corresponding chapters in the book, etc. So please make sure that you read these before you come to the lectures. Otherwise, it won't be very easy because I'm not going to explain all the details of these examples. I'll just be assuming that you have already read them from the book. So the first example is an emergency services call center. We all know what a call center is, I suppose. A call center is a telephone exchange, actually, where several people sit, operators, sit and wait for calls and answer these calls. These calls come in for an organization. So the call center belongs to an organization. And people, members of the public, who need to reach the organization with a query, with a question, or with some request, or with for some information, etc., they make a call. These calls could be for making reservations, for calling an ambulance, or whatever. Now, this one is an emergency services call center, so it is for, it's like a acute hospital where you have emergency clinics, etc. The operators in this call center are responsible for answering, recording, and checking calls. Checking means, of course, there may be false calls. A child may, for example, decide to call an ambulance just when he's playing. So you have to check whether the call is serious and genuine. A concern is, of course, to provide fast response. If there's a call, if somebody is having a heart attack and needs an ambulance, etc., you have to act fast. Otherwise, the consequences can be very serious. And the problem in the operation of such a call center, the call center operation is a well-known problem in operational research. I mean, people have published a lot of research on call center operation. The central problem here is, of course, to strike the correct balance between costs and waiting times. Now, by waiting times, we mean the waiting times that the caller has to wait. You dial the number of the call center, but sometimes you hear a recorded message. You have to listen to the recorded message and you lose time. Time is wasted. And maybe you get a busy message. Because all the operators are busy at that time, and you have to wait until one of them is free. So waiting time is important, and since this is an emergency services call center, waiting times, if waiting times are too long, then somebody may die, something bad can happen. So it is important to keep the waiting times, the expected waiting times, let us say, as short as possible. What do you mean by as short as possible? Well, you can reduce them to 0. 0 seconds waiting time can be reduced to 0 if you provide infinitely many operators and lines. There are two things you have to provide. You have to provide telephone lines, so that's the equipment. Maybe you have to provide a digital exchange, etc. So you have to invest money in hardware. And also you have to have people, operators who answer these calls. And both cost a lot of money. If you have many, many lines and many, many operators, there will be no waiting time. But there will be a huge cost. If you try to minimize costs and provide only a few lines and operators, the waiting times will increase, and that will cause other costs. So this is the difficulty in call center operations. The difficulty arises in the bold letters indicated, in bold letters, in the evaluation of the response rate. The response rate is the same as the waiting time, right? How can we evaluate? How can we put a money value, a monetary value, on waiting times? If waiting time is long, people will suffer. But how can we put a money equivalent to the sufferance of the people, to people who will face the health problems, serious health emergencies, etc. It's very, very difficult to put a money value on such things. So this is the difficulty, one of the most widespread difficulties in social systems. The way we treat these problems using mathematical models, etc., you know, are usually use what we call queuing models. This is a queuing system, a waiting line problem, a queuing problem. That's how we address using operational research techniques. But of course, the queuing theory on its own cannot resolve the difficulties that we have indicated here. I have seen a New York Times article last week where apparently the American government calculates the value of a life. I don't remember the exact value, but it's in the order of $4 or $5 million per person. And they have recently made a change in the value of life. I think they have increased it by 2 million or something. These are official numbers, I think, or numbers calculated by official authorities in the United States. And there was a piece of news about this. What's the value of life? Because people are insured, and if somebody dies as a result of an accident, and the accident occurs through the responsibility of some people, etc., they have to pay indemnities, etc. So I was thinking whether I should put these such newspaper articles and other pieces, bits and pieces of news and information onto the website for you to read. But then I hesitated. I said, well, if I keep loading the website with several items, the students will not be very happy. Would you like me to put those on the website? No. Yes or no? Anyway, you don't want it. Okay. So that's a queuing problem. A second example is vehicle scheduling. This is a very, very classical problem in industrial engineering and operational research. There are many companies operating what we call in Turkish cargo services. What these people do is that they have a fleet of vans or cars or whatever, and they have to every day they have a schedule of traveling to points of delivery or pickup. I mean, if I have a parcel to send, I would like to send this book to somebody in Istanbul. The delivery van arrives and picks it up and delivers it at the address, etc. So this is a question of how to schedule your vehicles, your cars. In what sort of routes they should travel every day, how many points do they have to make a pickup or a delivery, etc. So the pickup and delivery times will change. That will be, especially the pickup times will be dictated by the demand. The delivery times can also change because sometimes deliveries can only be made at certain hours. These are called time windows. There are time windows for deliveries and also for pickups probably. So there's a time window. I mean, you can make a delivery only between 5 and 6 p.m., for example, something like that. There are labor rules that you have to abide by, you have to obey. I mean, the drivers of these vans, of these vehicles, must have free time. They have to have time for lunch. They should not be driving for more than, let's say, 4 hours continuous, etc., etc. So there are labor rules, but then there are other difficulties like capacity and congestion restrictions. Capacity restrictions obviously relate to your vehicles, probably, and the number of vehicles and the volume of each, the cargo carrying capacity. But there are also congestion. Congestion means traffic problems. If the roads are congested, then again, you have to take note of this in order to be able to keep punctual time for deliveries and also for pickups. So this sort of problem is very classical in industrial engineering. There's a lot of literature published on such problems, many mathematical models, solution techniques, etc. This 20 factorial, as you can see, the 20 factorial is a huge number. It's an astronomical number. It just tells us that if there are 20 points from which you have to make pickups and deliveries, 20 points that you have to visit, then there are this many numbers of possible plans of visiting these 20 points. So you have to make a selection out of this astronomical number, the number of itineraries possible. It's a very complicated problem. And furthermore, you don't know what sort of thing to optimize here. What is best? I mean, what are we trying to optimize? Should we, for example, aim for least time? Least time means what? Least time of traveling? Least time for the customer, for the customers waiting for his parcel to be delivered? Is it least distance to travel, least cost? So all of these can lead to different solutions, and this sort of problem is also very is not easy, and it's not a straightforward problem to solve. A third example, as I told you earlier, please remember to read all the other details of these problems from the textbook. The textbook makes other points that I omit here. Make sure that you reach one other reason why you should be familiar with all these examples in the textbook is that in the quizzes and in the midterm and final examinations, I ask questions concerning these examples, assuming that you are familiar with these, okay? So please make sure that you read them properly. The third example is writing a mission statement. You remember that we started our course by showing you the mission of our industrial engineering department, and I told you that that we spent months, really months, to be able to write that mission statement. We started by holding a retreat. We invited 70 or 80 people to a meeting, brainstorming, etc., etc. After that, we wrote reports, and then there were 10 or maybe 20 different meetings at the end of which we were able to write that mission statement. So writing mission statements is a difficult and important problem. The mission statement itself should be relevant and meaningful. Mission statement, the writing mission statements has become almost mandatory in commercial organizations. With the advent of the internet and doing business through the internet, many rules have been established by the Ticaret Kanunu, the commercial law, the commercial code. Every company has to have a website, for example, according to the law. And furthermore, if you want credit from a financial organization, usually the way they appraise your, they evaluate your claim for a credit, sometimes works through international rules. They have to decide whether you are credit worthy, that is, you will be able to pay the credit back, has to be established somehow. And in many cases, they ask for a mission statement in the beginning and the strategy, because the success and failure of your organization has to be measured according to your own objectives and strategies, etc. So writing mission statements has become very widespread. And if you visit a hospital or if you visit any organization in the public or the private sector, sometimes you see a placard or something. Our mission is such and such and such. Even the websites say the mission is to serve humanity, to serve the customer. Most of these mission statements are very, very stupid, and they don't mean anything. So if it is to be useful, it has to be relevant and meaningful, mission statements. It should be achievable with measurable goals and targets. Active cooperation must be available, the cooperation of all the people who are involved in writing the mission statement, etc. It often involves conflicts and compromises. This is the important thing. Conflicts and compromises. Conflicts and compromises are the bread and butter of industrial engineering. You have to always to deal with conflicts and compromises. This is where you have to make a choice. The choice, the decision-making problem is a choice problem. It's always difficult. Why is it always difficult? Because you can never make a decision which satisfies everybody. Never. There will always be conflict. So, especially in writing mission statements, you have to face this reality. And lengthy, long negotiations and canvassing, lobbying, etc., is needed. This sort of problem is addressed by what we call soft operational research and problem structuring. We have two more. This one, the Deep Cove project, is a real-life example. It's from New Zealand, I think, the example. Dellenbach, the author of the textbook, is a professor in the Christchurch University in New Zealand, and the day before yesterday they had a serious earthquake in this town, in Christchurch. So Dellenbach got a PhD in America and worked a lot in American companies. Afterwards he became an academician and moved to New Zealand. So this is one of the projects he conducted in New Zealand. There is a cove, is a part of the sea which moves into the land, koi. In this cove, I think, there is a power station, electricity generating station, which takes water, fresh water, from a river, presumably, and uses it for cooling, cooling towers, etc. You find these in electricity generating stations, and then this fresh water is discharged into the cove, into the sea. The water is very valuable. It's fresh water and high quality water, and there was a project to take this water, tail race water it's called. Tail race means discharge from the station, power station, and put it into tankers and market and take it to markets and sell the water in the United States probably. There was such a project. But the cove itself is ecologically a very important area. There is marine life to be protected. The environment is very clean, and New Zealanders are people who are very, very particular about the quality of their environment. They pay a lot of attention to this. I know this because I went to Christchurch for a conference some years ago, and I had an apple in my pocket that I didn't eat. In the aircraft they offer you food, and the apple, I didn't eat the apple in the aircraft, and I put it in my pocket. They were nearly turning me back to Turkey because I brought the apple into New Zealand. They are very, very cautious about these things. No permanent residence in the sound. The sound is again the piece of water between two pieces of land pieces. I mean, if this project goes ahead, there should be no constructions, permanent residences built, because they will be detrimental. They will destroy the environment. The tankers have to move slowly, reduce tanker speed, because if they move fast, there will be waves and commotion in the water, and that's not good for marine life. Rubbish has to be removed, etc. So there are many, many such rules that you can try to implement in order to protect the environment, but there will be other risks. For example, there could be increased salination. I mean, if you take fresh water, which should be going into the sea, the amount of salt in the sea will increase because of the absence of fresh water. That's called salination. And increased salination is a danger for marine life. Mixing of fresh and salt water will be faster. There will be risk of spills. If you move a tanker in the sea, there's always the risk of oil spills from the tanker. Risk of introducing pests. Pests are mice and other vermin that you don't want zararlı hayvanlar. Poaching is like fishing without a permit, etc. So all of these difficulties will crop up if this project goes ahead. And there are others. So this is, again, a situation which is not straightforward. It's not easy to address such situations because there are conflicting objectives. One objective is, of course, to make money by marketing this water. But there are many other objectives, environmental objectives, as we have seen. This sort of problem is addressed in OR by what? What is MCDM? Multi-criteria decision-making models are usually used in such situations. But again, it's not straightforward to get an answer from these models. I mean, the models provide you with solutions, but these solutions are not the answer to your questions usually. You have to know, you have to learn and understand how to use those solutions in order to make meaningful proposals for solution. The final example is screening for breast cancer. Now, breast cancer kills many women every year. It's the most widespread type of cancer in women. It also occurs in men, male or female, but it occurs more in women. There are many types of breast cancer, but if they are diagnosed early, some types of cancer can be treated effectively and nothing happens, but the problem is early detection. So early treatment of growths is possible. Incidence rises with age. Incidence is a medical term. Incidence means the frequency of getting cancer. And this incidence increases with age. Older women, as women become older, the risk increases. If the cancer is detected at pre-invasive phase, pre-invasive means before it starts to spread with metastasis, etc. If a patient is diagnosed before this phase, then the chances of a cure is very high, 95%. So what do you have to do? I mean, who are you? Well, you may be a member of the women's group in the age where you are in the risky period of your life. You could be a doctor who treats cancer. You could be the member of you could be the Minister of Health of the country, etc. So there are many different groups of people who are involved in this sort of problem. So people or these people have to organize for making sure that early diagnosis and treatment will be possible. And this is possible by what they call mammography. Mammography is a special type of screening technique, X-ray technique, I guess. But the machines are constructed specially for examining the breast. And they are expensive machines. At the time of writing, each machine costs something like $200,000 to $300,000. And each screening in the United States, or I don't know, maybe in New Zealand, costs from $50 to $100. Each screening there's a variable cost and there's a fixed cost, in other words. So the problem is, how are we going to allocate the funds for this type of situation? The women's groups, for example, who might be initiating this project in a geographical area, in a regional hospital, let us say, where they don't have facilities for early detection, the citizens living in that area might initiate a project whereby mammography machines will be installed in the hospital, and in due time, all the population, one by one, starting with members who are at the riskiest period, will be screened, etc. But how many mammography machines are you going to buy? How many medical personnel are you going to assign to the operation of these? What is the best screening policy? It's a very, very complex question. Again, here the question is, how do we balance costs and human suffering? What's the value of a person getting, what's the cost of a person getting cancer? It's an extremely complicated problem. All these problems, so these 5 examples, as I said, are important. They are important also for you to get good grades. Okay, please read them. Have some common features. These common features, let's look at the commonalities of all these 5 cases. Each of them involves what we call a complex problem situation. So we are going to learn in the next lecture, which is a short one, what we mean by a problem situation. Obviously, it must be obvious to you somehow from all your previous experience in this department, but it is complex is important. The adjective complex is important, and we shall spend some time understanding what we mean by complex. In lecture 4, we are going to study what's called complexity theory, which is very, very important. So each one has is involved. Each example occurs, let's say, in a complex problem situation where it's not clear what the problem is. The problem is not very clear, you see. Are you going to schedule your vehicle so that the costs will be minimized? Are you going to schedule your vehicle so that the delivery time, waiting times will be minimized? It's not very clear what you are going to do exactly. Information is always missing. Information is always incomplete. For example, you need to know about the traffic conditions, the congestion possibilities, but you cannot have complete information at any time over all the entire road networks. It's dynamic. It will change from minute to minute. Another common feature of all these is that the situation is conceived as a system. You see, it's a screening, breast cancer screening system that you are trying to establish, or it's a cargo pickup and delivery system that you are trying to schedule. So usually what we are trying to do, we imagine it as if it is a system. This is what we mean by conceived as a system. Conception is understanding. You understand it as a system. So now, here we have a point of diversion. What do we mean by a system? We did not yet define what a system is, but even before we have a definition, we can point out the conception of a system. How can we conceive a system? Now, there are 2 ways to conceive, to understand what a system is. One is an ontological understanding, and the other one is an epistemological understanding. The difference between these 2 is important for systems thinking. Now, if we assume that a system is an ontology, what do you mean by ontology? Ontology is a branch of metaphysics that studies the nature and existence of reality. What does it mean to be? To be. I am. I exist on this earth. What does it mean philosophically to exist? These questions are philosophical questions, and the area in philosophy which is involved with these questions is called ontology. Ontology. It's also used in recent years in Turkish, in newspaper articles, magazines, etc. You can see ontologic. It's used as in Turkish also. So ontology is an area of philosophy. And if we treat a system as an ontological entity, we mean that the system exists out there, out of us. It exists out there independently of us. What does it mean? It means even if I am not here, the system will be there. It's part of reality. If we are all dead, for example, the solar system will remain and will continue to exist. So the solar system can be regarded as something which is independent of human beings, or our perception, independent of our perception. It's part of reality. This is the normal way of understanding what a system is. Probably you all regard systems from this point of view, because you are used to talking about inventory systems or production systems or marketing, etc. All these areas of industrial engineering applications are known as systems. A transportation system, for example. But when I say transportation system, things start to get complicated. Is a transportation system independent of us? Well, parts of the transportation system are roads, for example, or trains, or automobiles, etc. And an automobile can seem to you, can appear to you as if it can go on existing even if you are not there. But why is the automobile there? If I were not here, the automobile would not be there. I made the automobile in the final analysis. So this ontological perception of systems may not be sufficient in all cases. The other one is the epistemological. Epistemology is another, is again a branch of metaphysics or philosophy that studies the nature of knowledge about reality. Ontology concerns existence, and epistemology concerns what does it mean to know. If I know that I am alive, what do I mean by knowing? This is questions such as these are the domain of epistemology. The methodologies and system thinking actually is part of epistemology. We are not going to discuss the philosophical foundations of operational research too much in this course. I tried to do this in the first few years that I taught this course, but it caused a lot of difficulties. So we are going to minimize the philosophical content. But you see, industrial engineering is a profession which is not independent of philosophy because it involves choice. When you have choice to make, of course, an electrical engineer also has to make a choice. But the choice of an electrical engineer could be about choosing between different designs of making and constructing an antenna, for example, which is a technical problem, and the choice there can be made more easily. In our case, the choices are always difficult, unfortunately, because they involve humans and different purposeful systems where you have individuals having different goal-seeking people, etc. So epistemology is concerned with the theory of knowledge, you can say. And if we regard the system as an epistemological entity, we assume that the system is not out there, but it is inside us here as a mental construct. Okay? So both are possible. And as we shall proceed in the course, we shall argue that the second way of understanding is much more important for us. It's a mental construct.